In this video, I want to talk a little bit about how LLMs, or large language models, which you might think of as like ChatGPT or Gemini, and I want to talk about how they work. So obviously, like most of us probably already have used ChatGPT or something like it. The way it works is you ask a question and you get a pretty good response, or you ask it to fill in a blank and it fills in the blank. Now this is how they work, sort of as from the user side of things, but let's talk a little bit about sort of the technical side of things and how they actually work behind the scenes. And before I jump into large language models, I want to talk a little bit about what are Markov chains. Markov chains are kind of the baseline of how these tools work, and I think by understanding them at a smaller scale, then we'll be able to take them to a bigger scale and understand that. So if you're a certain age or old like me, you might remember that Twitter bots had this really big thing happening in sort of the late 2000s, early 2010s. I think lots of people on Twitter were making bots either of their own work or of other people's work, taking famous poets and then turning them into bots or whatever. And usually these were happening because of Markov chains. Unfortunately, many of them either no longer post or have been removed outright. That's because when Elon Musk bought X, he decided to start like charging for these things, and most people were doing them as fun side projects. So most of them are dead now. Sorry. Kind of annoying, but so it goes. And I think what's really important to understand is that we've talked a little about shallow AI versus deep AI. Markov chains are very simple, and they are essentially shallow AI models. And what they really do is they basically try to create the next word in a sentence or in a phrase or whatever using probability scores. So we'll talk a little bit about how they work. So the first thing you need to do is actually download what we call a corpus of data. That could just mean a bunch of text. So for something like the tweet bots, you would often download like a CSV file of tweets. So it would be, you could go in and export your data, get all of your tweets, or get all the tweets of someone else, and begin to save that into the system. Now, what it does, it goes over all of the data inside of these files and sort of learns, quote unquote, how to structure sentences like that the tweets that are given to you. So in my case, there's probably like words and phrases that I use that other people don't, or there's weird sentence structures that I use that other people do not, and it would sort of learn that. And the way it would learn that is basically by looking at all the words in sequence and sort of understanding the probability or the likelihood that one of those words would follow another word. And then we basically reverse engineer that process. So first thing it's going to do is pick a word more or less at semi-random, right? So it's going to look at all of the first words that were used in my tweets, and it's going to pick one. And it can often be quite random in how that works, but it would just pick a word. So let's say it picks the word it. The next thing it's going to do is, based on this word, it's going to then try to figure out what the next word should be. And this usually happens by looking at probability scores again. So it's going to look at what's the most common word in that corpus that follows the word it. And then it will assign a probability score. So there's a couple options here. It could be it is, it was, it never, it always. And you'll see those P scores, which means probability, alongside of them. Now, the important thing to know here is that it's not always going to pick the most probable word. In fact, what often happens is it injects a bit of randomness. So it's going to pick from maybe the top 50 words, but it's never going to pick always the most top word, because all that will end up happening then is going to repeat the same phrase over and over again. So in this case, let's say it randomly picks it was. It then does this over and over again, right? So it's going to say, based on it was or based on was, what's the next word? So it was just, and then just what? Just me and. So it just goes through the sequence one by one. And you'll notice here, I sort of made up this sentence, but you'll notice at some points there's like a weird break where then the words become sort of indecipherable, right? And that often happens at words like and or other things where basically it structures, an and is such a common word that there are so many options after it, and that can be a point where like the sentence kind of falls apart. And that's the reality of Markov chains. Markov chains tend to produce very weird text. So if we look at the examples that we've shown before, if we go back here, you'll see that this Markov bot here is like very, very weird. Of childhood home with pride, like I don't even know, like it's not a sentence, not a phrase, it just is like a gobbledygook of words. And likewise, like my bot is probably a little bit better. We'll talk about why that is in a minute, but you will see that it still is pretty confusing. And that has to do with how Markov chains work. Again, I mentioned that it looks for the previous word. In some cases, it looks previous couple words. So it might be the previous 2 words or 3 words or 4 words. This is what's called the context window. We'll come back to this because context windows are also very important in LLMs. And actually, the reason that LLMs work so well is actually because of their context window being different than that of Markov chains. So Markov chains look at very small sections of words, right? So in the most basic case, it could just look at the previous word before it. But in a lot of cases, it actually looks at maybe 2, 3, 4, 5, 6 words beforehand. And that'll give it a little bit of a better structure, right? So instead of it just picking a just word after, the word after just, it'll instead look at was just. And that might give it a little bit more of a coherent sentence structure. But again, as I mentioned, when you hit stuff like me and other things, it will often create different and weird context or different words for that after. And that's how you get some of that craziness in that system. Now, with Markov chains, you can set the value here. So some people who want really crazy values will actually set it to 1 to purposely get weird results. Whereas, people who want a more coherent language will often set it to the widest context window that the model supports. Another key thing about this is when you think about this idea, Markov chains don't scale well, meaning it works well off of a bunch of language that I've written or a bunch of language that maybe Shakespeare's written where there's some commonality in the way they talk. If you were to scale this to all poetry, it would go crazy because every word combination or probability is likely very, very different. So because of that, these Markov chains don't really scale well. And obviously when we talk about LLMs, we want to talk about scaling. We want to be able to talk about, being able to do anything with these tools. So therefore, Markov chains don't really work. And you'll see here, again, this example of the Markov bot, which apparently pulls, I believe, from the top 100 accounts on Twitter. And it's all over the place, right? It says Trump, and then it's like where your alarm goes incognito at her most in history. Now, again, this Markov bot might also be using a very small context window to generate sort of the chaos. But regardless, even if you were to pull from the top 100 accounts, which might be, news accounts or other places, you will get a lot of chaos because just a lot of data that isn't similar in the way it's structured. Compare that to maybe my account, which is, a little bit more of just me, and it will create a little bit more of a common language because it's a little bit less data and it's a more common, it's just me and the way I speak. So that gets us to, let's start to talk about LLMs. So obviously remember that when we talked about these models, they're shallow AI, right? So we've got a shallow model here. And then when we talk about LLMs, we're going to talk about what are called deep models. And again, the way to think about this is just that there's actually way more layers here. And we'll talk about a little about what these layers could represent in analogy when we get into LLMs a little bit more. So let's talk a little bit about how Markov chains and LLMs differ. And again, the LLM stands for large language model, and the emphasis is on large. We're talking about big, huge, massive models, right? These take months to train, they cost a lot of money to build, and then they're able to do a lot with them. So the emphasis we're going to talk about here is on the large and the scaling part. So as we mentioned, the Markov chains are pretty shallow AI, whereas LLMs are deep AI. Again, it looks like this. So we've got the shallow side here, we've got the deep side here. Now with deep models, it's important to remember that each one of these nodes is what might be referred to as a parameter. So in a shallow model, there might be, very few parameters. This might be, word and its relation, probability that it's after this word, and then you get the output. Whereas with these models, there's so many different parameters. How many parameters are in some of these models? Well, let's take a look at that. So I've just quickly done some research into how many parameters are in each LLM model. BERT, which was made, I think, in 2018, has 342 million parameters. And that sounds like a lot, but it's actually quite small in comparison. Gemini, which is the newest model that's come out from Google, apparently the smallest version has around 3 billion parameters. So we don't know, they haven't really announced how many parameters are in these bigger models that they released, but we can say at least over 4 billion parameters. Llama, which is from Meta and Facebook, is 65 billion parameters. Claude 2, which is from Anthropic, is 130 billion parameters. And then the largest version of ChatGPT 4 is rumored to be about 170 trillion parameters. I don't even know how to accurately like think about 170 trillion parameters. You could not draw that in this map; it would be insane. But let's talk about a little bit like what these parameters might represent. Now, this is an analogy, not exactly how I would expect to describe this, like in the model itself. But a way to think about this is actually that the model builds up as it goes, right? So it might start with words or even letters, and then as it goes through this process, it builds up these phrases, sentences, paragraphs, all the way up to pages. So again, these models do represent structures, right? They think about building blocks. And usually what happens with these models is they start very basic and they get more complex as they move through the model. Now, this means it can represent far more complicated phrasing structures, far more complicated data itself. Again, these models are far, far smarter than Markov chains. Markov chains just understand it at the word level, but these models understand it much more at a higher structural level. And the argument is like, do they understand what they're actually saying? I can't speak to that, but I think there's some argument that like by knowing this much about a structure, they do inherently represent what they are saying and the data they're providing. Whether that's true or not is a slightly different topic, but they are representing a large model as they go through this system. Okay, so we talked about the type of model. Now we're going to talk about the context window. So again, remember, context window is how far back it looks. The context window for Markov chains are words. LLMs, as we started describing with those deep models, are much, much larger. In LLM language, if you're looking around various websites, you might see the word referred to as tokens. Now, tokens are essentially the context window that you might see in Markov chains. Tokens are a little bit more of a complicated topic, but I think it's fine to think about them as an individual word, even though that's not always accurate. Sometimes it's like partial words, like you could think about, with stuff like verbs, there's different verb phrasing, like past, present, future, like those sort of things. Like, so sometimes the tokens break down on that level even. And just for an example, ChatGPT 4 supports 8,000 tokens. So you can think about it as 8,000 words. So our Markov chains are like one word, maybe 10 words at most. ChatGPT supports 8,000 tokens. And in fact, the newest version of Gemini Pro, which is slowly rolling out to people, supposedly supports 1 million tokens. I don't even know what 1 million words, I don't know how many words are in like a book. I suspect it's less than a million. So we're talking like a context window that is so huge that it probably will remember every conversation you've ever had. You might notice, if you've used like maybe ChatGPT 3.5 or some of the older versions of these models, you might notice that after a certain amount of time as you're talking with this bot, it forgets things, right? Or it changes, some of the initial details. That's what happens when you run out of your context window. So context windows are important for memory, essentially. I don't think it's good to say that these models have memory, but that context window essentially acts like a memory system. And if you've got 1 million tokens, you're likely going to remember everything you ever said in a session with that bot, or the bot will remember that. And that's probably better for stuff like these bigger conversations. I expect to see this get even crazier, but at some point, I don't even know if there's a point in having this many tokens in memory. So let's talk about the training process. So as we mentioned, like Markov chains pull in that like a CSV file. LLMs are crazier. We're talking about, it's unclear what a lot of these LLMs are actually trained on. ChatGPT being a private model, they don't tell you what it's been trained on. But we know for sure it's been trained on a large corpus of web pages, on the internet. So lots of documents. I imagine they're pulling book data. If you think about Google Books, they're probably scraping Google Books and that content. They're probably also going in and doing stuff like looking at videos and pulling out video content. There are now models that'll take a video or take audio and convert that to a transcription, and you can feed that into these models as well. They are text-based, so everything has to be text at some point, but it's pretty easy now to convert between different media types into text. So fair to say, this is much, much bigger than a single CSV file. A lot of the open source LLM models that are out there usually train on what's called the Common Crawl dataset. The Common Crawl dataset is a dataset that crawls web pages. Basically, if you've ever seen that norobots.txt file, that basically says you're allowed to scrape this website. The Common Crawl scrapes pretty much every website. As of, I think, 2023, that meant 3.1 billion web pages. And that could be, short text, it could be a really long text. So suffice to say, these are trained on very, very, very large corpuses of data. And in addition, ChatGPT is also like multi-stage training. I would assume other models today are doing something similar, but they might not be doing exactly what ChatGPT does. So first off, it's trained on that corpus of data, right? But then you remember that this is actually a chat structure. This is a model that talks back and forth to you in a chat. So there's actually a second stage that is called what we call supervised, meaning a human interacts with the machine and says, no, you phrased this wrong, or you did this incorrectly, and sort of scores the model based on how well it's doing. That also leads to this chat structure, right? The ability to create this chat structure happens because of this second stage of processing. If you think about Markov chains, do not chat. Markov chains just complete sentences. So this model has been particularly trained in order to do that sort of chat infrastructure. There's also then a third stage, which is what we call unsupervised, meaning there's no human involved in the process. And this is also a thing called reinforcement learning, which we won't get to in this video, but reinforcement learning is, I don't know, I would almost describe it as like an animal learning. I guess you've heard about the mouse that gets a treat all the time, whatever. It's sort of like giving a machine learning model a treat, and every time it gets the treat, it gets something right, it gets a treat, and it learns to try to do things more correctly as it goes through it. So ChatGPT is likely the most complex training publicly available. There are probably systems that are not public that we don't know about that have been trained in a crazier way, but ChatGPT and maybe Gemini are probably the most complex training systems available today, and that's why they tend to perform so well, because these multi-stages means it's been built up and learned, quote unquote, at such a massive scale and done in such a way that they really learns a lot. Now, as part of that, we also talk about the cost of these models. A Markov chain today, you can run like a Python script and it will basically generate a Markov chain for you. It is essentially free. Even back in 2010, the reason people were making Twitter bots is because they were essentially free to make. Now let's talk about LLMs. We're talking in the millions or even billions of dollars to train these models. So OpenAI said ChatGPT, I think this is with ChatGPT 3, costs about $100 million to make or to train. Gemini, there's some reports that it might have even cost up to $3 billion to train one of the Gemini models. Now, this is probably a difference between, I think what I heard about the ChatGPT model is this is how much it costs to train, meaning servers, whereas some people might be saying Gemini involves like the human costs, like the purchasing of data, et cetera, et cetera. So it's a little unclear how these numbers match up to each other. But regardless, we're talking money that you and I can't spend. We're talking about money that only Google and OpenAI and Facebook can spend because they have it. So this is a huge difference in you and I can make a Markov chain, but we can't make a ChatGPT model. Now, fine tuning, making your own GPT, all that stuff we'll discuss in future videos, that you could do, but it's taking this massive model and sort of slicing off a little piece of it for yourself. So again, there's no way a human, an individual, could actually afford to make these models. And that's why they're so powerful, but also kind of why people are a little bit afraid of them, because they are not accessible to you or I. Next, we're going to talk about modalities. So by modality, I mean modes. This is either text or image or tabular data or video. Markov chains can only work within one modality. There are actually Markov chains that will produce images. Just like with the text, they're pretty poorly created images. But Markov chain, as I mentioned, is just an algorithm. It uses probabilities to create one thing and then the next thing. So you could think about that as pixels in an image. You could think about that as music notes. So they can produce any number of media, but they only produce one type of media. Whereas with LLMs, we're going to talk about what's called multimodal, meaning they can combine different modes and different media types together, right? So the newest release of Gemini talks a lot about how you can feed an image and get code back on how to produce that image. Or a video, I guess in this case. So you give it a video of birds flocking, and then Gemini produces a flocking simulation. That's kind of game changing. We've never really had a world where we could show a model a video and get code out of it to produce that video, or to something like that video. That's really fascinating. It is one of the things that Gemini really purports to do well. My experience, hit or miss, but it's at least an option. Obviously with ChatGPT, In ChatGPT 4, it can read in images. So you can send an image to it and say, like, what's in this image. But now with DALL-E's integration into GPT-4, you can also make images. And then you use the chat structure to actually change your image over time. Again, these are very drastically different sort of tooling because we're not used to using text to generate an image. Usually you have to go into Photoshop and paint some stuff in, that sort of thing. And now we're basically doing this multimodal thing to produce different media types, either text to video, text to audio, text to image, like text to text, or images to text, or images to audio. Like these sort of translational tools are going to become really, really powerful in the future. And it's one of the powers that LLMs have over a lot of the other programmatic tooling out there. And lastly, I want to talk about a little bit about what we call control, right? You and I as users, how do we control these things? With Markov chains, it's pretty basic. The Markov chain, you say, here's how much is the context window, maybe here's some of the randomization levels you have, go at it, like, create me some new text. Whereas with LLMs, we've got so many different options to create different models. And one of the big ones is prompting, which we won't talk about this video, talk about prompting in the next video, but it is a really important control tool for LLMs. So I do want to talk about a couple things within LLMs that you can play with. One note is not every model allows you to play with this directly. So there's a thing called temperature. And if you remember when we talked about Markov chains, we talked about there's the probability, but then there's also selecting from a random assortment of those things. Temperature, as defined in LLM, is actually a way to select the amount of randomness in a token selection. So if you crank up the temperature, you're going to get a really weird result. If you crank down the temperature, you're going to get more of that likely probable text scoring, that sort of thing. So here's some examples of temperature at play. So I think the default score is usually around a 0.8, 0.9. So if I ask, what is a cat? I get a pretty basic response back, right? I would read through this and be like, yep, that sounds realistic. It generally provides content that you would say is like realistic and written in a normal sort of professional manner. If I crank my temperature up a little bit, you'll see it gets a little bit weirder, right? So if I crank this up to 1.5, you'll start to see there's some weird selections of words in here. 190 million. 90 is not like a word, but it also is like kind of confusing. You can kind of understand what it's saying. You also tend to get bigger like words that then need to be defined. Throw in stuff like scientist names. It starts to feel pretty weird. But now let's go real crazy and crank it all the way up to 5. And here you'll see it just goes off the rails, right? The first response is, oh, sweet goodness. And then none of this makes any sense. It's literally like a cat talking to you. It looks like there's all sorts of, weird tokens and language in here. And honestly, I don't even know if any of this is actually real words. So this shows you the level at which you could crank this thing up to get quote unquote more creative or weirder results. Now, obviously, I don't think most people are going to crank this to 5.0. But if you want to, just to sort of see how crazy the model gets when it is allowed to accept anything, essentially, this is what you can do. There are a couple other parameters in here called top P and top K. I wouldn't worry too much about these. These are essentially different ways of selecting from the probability set. So top K, I think, defines the top number of probable scores. Top P defines it based on like the actual probability itself. So if you want something that has a very, very low probability, you might set top P to be a little bit of a higher score, so you can include it. Top K is like the top 50 results, right? So you want to grab from the top 50 or the top 100 or the top 200. There's also an option for max tokens. Again, remember, tokens essentially mean words, and this is the amount of tokens in the output. So say you want a shorter result, a longer result, you can set that as well. Most LLM platforms, especially like ChatGPT and Gemini, do not actually provide you direct access to those variables. In fact, instead what they give you is something like this. So this is Gemini. So you can modify the response by shorter or longer, maybe simplify the language or make it more casual or more professional. These are probably essentially accessing those variables or adding some additional prompt, engineering behind the scenes to produce something that gives you a little bit more of a professional tone or something. This is why sometimes we prefer open source models. Those of us that like to play with these tools a lot do like open source models because I can literally, in Hugging Face, for example, I can go and look at what Llama's model is, which is again from Facebook, and they've open sourced their tools so anyone can use it. You can go in and crank up the temperature score. You can crank down some of these other things. I didn't even talk about repetition penalty, but you can like essentially penalize the model if it repeats a lot of words or phrases, which is a thing that happens quite commonly in these tools. So having access to open source does give you more availability, but it's obviously at the cost of convenience. So it's easier for me to come in and change one of these things, but I'm kind of also playing on my own world, and a lot of like ChatGPT as well as Gemini these days have a lot more like interesting functionality built on top of the LLM itself. And lastly, obviously prompt engineering is a huge controlling factor. So if you want to learn a little bit more about prompt engineering, I assume everyone sort of knows a little bit about how prompt engineering works. But my next video is actually going to cover all about prompt engineering. But suffice to say, like, you can gain a lot of control by learning to speak, quote unquote, speak the language of these machine learning models. So in the next video, we'll look at prompt engineering, but I do think it's important to recognize that is a major control factor within these tools. So anyway, I hope you learned a little bit about LLMs in this session, as well as learn a lot about Markov chains, and maybe you'll be inspired to go back and make your own Twitter bot, or maybe you'll just stick with the newest model in the LLMs. So that covers everything I want to cover in this video. So again, next video we'll look at how to do prompt engineering and what is prompt engineering.